All right, guys, almost ready to go. Slider's giving me some trouble, but I think the code at least worked. Let's see if we can work with it in that way. Here's today's code, as always. Right. If you have questions about the Bamboo assessment, let's put that to the end of today. Try to leave some time at the end. Okay. I hope it'll work out. So welcome back, everyone. Welcome back to COMP526 efficient algorithms. We're starting a fresh new topic. We'll talk about strings for a while, not just this unit, but we'll start nice and simple. So I'll talk more about what strings are for us, and then specifically this unit will be about string matching, finding subsets in a large text. Again, something some of you will have seen. We'll then build on that and go a little deeper than you would usually go. The learning outcomes for this unit are know some basics about strings. If you haven't seen this before, it's just something ubiquitous in all of programming computer science. There's a few concrete algorithms we'll look at, the Knuth-Morris-Pratt, Boyer-Moore, and Rabin-Karp algorithms. That's what these abbreviations stand for. And as always, like for the sorting unit, I want you to not just be able to execute the algorithms, but understand when they are good and when they're not so good. And we'll look a little bit at building blocks that you can use to solve other problems, because it turns out people don't always just want to find substrings. Big surprise. I subtitled the unit as What's Behind Control F. I mean, for all Mac users, whatever the shortcut is there. Today, you could even say what's behind search. That would just be slightly bit lying. Think of this as finding the text in a text editor. It's a little different if you have a search engine that can pre-process the text, but we'll come to that as well. I want to start with some basics about text and string. And although this is quite elementary, the formal way to define strings and work with them in a mathematical setting is it could be new for a few, so I want to briefly recap that. For us, a string is just a sequence of characters. So you hopefully know what a sequence should be. Now, a character can be pretty much anything. We'll come back to more restrictions on that. Some examples of where strings arise, any kind of English text or other language text, source code and websites, and pretty much everything essentially is converted to a text because it is a very natural format for us and computers. Despite some exceptions, much of computers is one-dimensional in a way. We organize memory one-dimensional, and so it's quite natural to also do this for the data that we work with. And some things like XML documents, they're effectively a tree, right? It's a tree structure, but you can encode it as a text. And so many things we do for text are a little more general than they first appear because you can map so many things back to text. Okay, when I say text, that's the same as string. It's just, I don't know, a string sounds short and text sounds long, but there's no formal difference. Okay. Because it is applied in so many different contexts, it's not surprising that there's different requirements and different algorithms depending on what you want to do. the task we will focus on for this unit is to find a short pattern in some long text. So we find exact occurrences of some pattern string. And so that's what usually Control-F, at least in the text editor, does. Many searches are slightly smarter these days. They try to also find things if you mistype them, or at least if you mistype them in the typical ways that other people have mistyped them. But we'll focus on the exact one first. There's a classic Unix tool, grep, that basically does this and more. fgrep if you want to be specific. And at least the core of virus scanners still works like this. They also have additional heuristics, but they still have signature databases where they have little snippets of machine code that they are looking for because these are known to occur in known viruses. So they're really looking for substrings exact matches as their core principle. And the reason why they still do this is that it's so fast. Many of these other heuristics are smarter and better at finding threads that are slightly changed from what has been seen before and so on and so forth, but their basic text search is so fast, it's still useful as a baseline. Yeah, as for sorting, it's often a building block for further things. So what are strings for us? I already said it's a sequence of characters, so we should know what a character is. And we'll just talk about alphabets. So here's the first Greek letter of this. It's a capital sigma, same as the sum sign, but not the same symbol, right? It's a Greek letter, capital sigma. We use that to denote the alphabet. The only thing we really restrict here is that it should be a finite set. So you can write down the alphabet once and for all. It's convenient to have a notation for the size of the alphabet. So that's the little sigma, or at least one version of it. So we use these two, keep that in mind. Standard types of alphabets are just the letters we use in English and other languages, but it could be a bit bigger. Could include all the emojis. I forgot to look up the latest stats. I think it was around 200,000 characters in the Unicode standard. Maybe I'm exaggerating a bit. They keep adding more emoji and more more other super valuable things, all the Klingonic scripts and whatever. But even if you are very liberal and include anything and everything that some group of people says, yeah, this is a thing, you end up with something like 200,000. It's a lot of characters if you wanted to write them down, but it's also just 200,000 if you think about it. In terms of computer memory, it's not such a big deal. There's much smaller alphabets as well. This is from bioinformatics. Your genetic code is basically a 4-letter alphabet. All right, many different alphabets, and we'll usually keep that generic. We'll just say there's an alphabet sigma. That's a single character. Now, to form sequences of these characters, we have different notations that are handy. If you just say sigma with a superscript n, you can say that's just the n-fold Cartesian product of this in set notation. So that's all n tuples. So it's all strings of length n characters. So you can write that very briefly as sigma to the n. People have these two abbreviations that are handy. Star means any n, and you take the union. That's what's spelled out formally here. And that includes the string of 0 characters, which is called the empty string. So we'll have a separate symbol. I'll always use this epsilon here to denote the empty string. It's just sometimes useful to write that. All programming languages would use quotes for strings. All that I can think of use quotes for strings. And so the empty string would just be quote, quote. To not write quotes all over the place, and you know all the hassle with escaping if you need the quote symbol inside a string and all that. In the mathematical notation, we don't do that. We don't normally write quotes. So that's more concise, but it means you can only write the empty string if you have a special symbol. The plus as a superscript is the same as the star, but starting at 1. So all strings that are not empty. And then because a string is a sequence, we will model this as an array in a computer. And so the rest of the notation is derived from that. I'll write this bracket notation to say that's the ith character, but we start with 0, which is exactly what Python does, right? A string in Python is an array of characters, and so in square brackets 0 gives you the first character in the string. All right, just a few more. So if you have two strings, you can just write them behind each other, and that means concatenation. Now, it's a little unfortunate that in math terminology, the dot as multiplication is what people predominantly write for concatenation. This comes from group theory, and that people thought about strings as the free group over the alphabet and so on. And so the natural symbol for groups there is multiplication, not plus. I mean, this is a very weak justification, but it's very firmly established. So if I write two strings and put a multiplication between them, that's concatenation. Python would use a plus. And most programming languages would use a plus. So that's just, I don't know if it makes a lot of sense to add this to the slide as well. I don't think I'm telling you new things at this point in the term. Last piece is, if we have a string, we will often want to speak about substrings, which is a contiguous range, so a subrange of the array, same as we used for recursive calls of sorting algorithms. And so Sij is the substring where we include the endpoints, and we'll use this notation often as for arrays. So same, just different names for it. We call it a substring here. And two specific types of substrings are prefixes and suffixes. A prefix is a substring that starts with the first character or at position 0, and a suffix is someone that goes all the way to the end. All right. Any questions on the notation so far? My suspicion is that much of that is repetition, but just to have a little check, let's do this little one. Just two answers, so I realize you can just guess, but maybe avoid the guessing. We've had a record-breaking 81 votes on the attendance code. So let's see. So we should definitely get 60, right? Or more. Mysterious where these 80 people are. It's not a trick question, so I think I'll leave it with 46. Most of you seem to know that that's the same, and that's true. Just to recap, so this is the set of all strings, including the empty one, so you can write this as non-empty strings and the empty string. All right. So what do we want to do with our strings? Let's formalize this finding patterns as well. And there's one caveat here where indeed you have some choice. So I'll point that out. The first is just the names. So we have two types of two strings involved in this problem. The input is a text and a pattern. So T will always have length n. So with our new fancy notation, we can write it like that. And the pattern has length m. So that's where the two letters come from. And I'll use that same names on many slides. So just hope that sticks. We usually think of the pattern being relatively short and the text relatively long. But that's not something that's part of the definition. It's just if you think about what are typically good algorithms, that's something to keep in mind. But it's not to say that you always have this. Now for the output, this is a little ambiguous. So what we define here is we want to find the first occurrence or the first match of the pattern in the string. So that's formally the smallest index I, so that the pattern occurs starting at this position I in the text. All right. Now, what would be the other option? It could occur several times, so you could just report all the indices. Then you can get into a question, what about overlapping occurrences? If the pattern allows that, do you count all or both? So for here, we'll just break ties, say the first is all we want, and if you want more, you have to continue searching. Again, that's something in line with most programming languages. Python has this find function on strings that does, by and large, the same thing. Of course, it can happen that there's no occurrence of p in the text, then there's some special return value. We'll just call that no match. You can also find all. We'll touch on that briefly later, but for now, you can just do this iteratively by asking for the first occurrence and then taking the suffix of the original text and continuing from there. A quick example, here's a text and here's a pattern. Now our problem says find the first occurrence. And so he occurs here. And remember, we start counting at 0, so that's return value 1 because that's at index 1. And for another pattern which does not occur, you should return no match. Okay? Good. So far so good. Let's hammer this point home. But I want this real quick, so if only the connection will work. Let's try to do this real quick because it's a simple question. Should have probably hidden the results. Either way, no one disagrees, so to not bore you to death. If you write the indices above each of the characters, then you see that position 3 is the P, and then you go up to position 7, but excluding position 7, that's the round parenthesis. So you take positions 3 to 6 inclusive, so that gives you P5 to 6. Okay? Not too hard. Okay, that's just, there's so much confusion in the literature, so maybe let's flip that over into a warning. If you read up elsewhere on strings, always watch out for do they start at 1, do they start at 0, are inclusive, the substrings inclusive or exclusive of the endpoints. There's just no consistency, so you always have to be a bit careful. Of course, it doesn't change the fundamental principles at all, but well. Maybe at this point, before we continue, let me ask what kind of string matching algorithms you've seen, so I can get a feeling a bit for how fast we should go over this unit. I'm aware that there's always a few people who have not seen any of this at all. In a way, my justification at MSc level is that it's fairly fundamental things. So even if you haven't seen them, by now you've learned to digest this content faster than undergrads. And for those who have seen it, yeah, I love this specific string matching algorithm. Well, I mean, algorithm, what I mean by algorithm is the way it works, not necessarily boasting with all the languages you've learned and how the string search method is called there. Okay, again, it's tough to see from there. So brute force, 9 people voted. 5 people noted none. We're still just at 33, 34. So if you're done voting, send your favorite emoji. Is that our signal? I'm proud of you guys. No poop emoji so far. All right. Pardon? It might. It might. You don't have the balls for that. All right. So we have 16 brute force, 6 none, and a few isolated votes for others. So I'll leave it open. Yeah, I'll leave. How distracting is that for you on the phone to keep it open? So let's not rush it too much. If there's a substantial fraction of people who have not seen it. But many of you have seen brute force. I guess I triggered your memories, right, by putting that up. Either way. Right. So let's see a few string matching algorithms. Maybe memories will come back. The first string matching algorithm I want to show you is called the brute force algorithm. And normally this means it's a terrible solution. In this case, it's not so terrible. It's still useful. And so it's a fine algorithm, but it's worth knowing its blind spots. Before we get to that, it turns out that a lot of different string matching algorithms can be cast in one framework. So let's introduce that a bit. Most of these algorithms will work by making a guess, and a guess is just a position in the text where the pattern could occur. And then you might check individual characters, one character from the text and one from the pattern. Do they match or not? I think it's conceivable that this is what you will do in string matching in one way or another. You have to start making some comparisons somewhere, and then you do several checks to potentially verify a guess. The number of guesses is not absurdly big, so that's why brute force has some hope. A little thing to keep in mind, if you want to verify a specific guess, at one point or another, you will have had to check all the characters of the pattern. So it needs m checks. But it might be enough to do a single check to dismiss a guess. If, for example, the text contains some symbol that does not occur in the pattern, if you find that symbol there, you know there's no occurrence. You don't need to check any of the other characters. That nicely leads us to a useful cost measure. So remember, this will come haunt us many, many times. The word RAM model says we should just count all these primitive instructions, but we don't often feel like coding at that low level. So instead, we count something that's the same for all these possible conceivable implementations, some abstract cost measure. And that's the number of character comparisons in this case, so the number of checks. And if we're not doing redundant checks, Now, okay, a really stupid algorithm could well do more than these checks, but non-redundant checks, if you manage to keep note of the results, you should not do more than n times m, because that's every possible position in the text against every possible position in the pattern. You've learned everything after that many checks. Nothing new under the sun after that. So how would the brute force method work? It checks all guesses. And the only slight bit that's smarter in this is to break out of the loop a bit early. But let's just first do the example. So the text is written up here, and the pattern is ABBA. So I already filled out these diagonals to show, to help me not to lose track of the lines, but also to show you that's the worst that can happen. For every possible starting position, so in a way, this is the starting position here is I, that's 0, 1, 2, and so on. You have to do at most 4 checks because that's the length of the pattern. So if we start comparing here, A matches, B matches, B matches, but then we have another A, so we have a mismatch here. So that was not a correct guess. Too bad. Let's start from the beginning. So do another, oh, okay, it doesn't match. Another, it doesn't match, doesn't match. So in all of these cases, after the first check, we could already dismiss the guess. And if you look at the code above, this is also what it does. It goes through all the guesses, and then it goes through all the positions in the pattern and compares the appropriate positions in text and pattern. And if they don't match, then you break out of this loop. So you don't continue comparing if there's no need to. If you reach the end of the pattern that way, then you return your guess. And that was the first hit, the first occurrence. And if that doesn't happen, so if you didn't get all the way to the end of the pattern, then you would not return a match and continue with the next guess. Let's finish this off in the example. Here we have a match, A, B, but then there's another mismatch. Mismatch, A, B, B, A. Hooray, we found our pattern. Let me just mark the mismatches as well. Okay, and here's the thing in nice again. I did the counting for you, so it's overall 44 comparisons, character comparisons that we needed in this execution. Sorry, it's 15 out of 44 character comparisons that we needed. 15 we actually did. 44 would have been the worst case, all the shaded cells. So it doesn't look like brute force is doing too badly here. Okay. I think this is still true in Java. Is essentially this method is what they use. It's only mildly embarrassing. Python has a much more sophisticated method. They used to have something that's fairly close to something I'll show you, and now a few years ago they had a specific project where they asked algorithm engineers to come up with something better. So now they have a quite customized, sophisticated method. So definitely not doing brute force. Now this sounded like brute force is not such a bad idea, and if Java does it and people are not always complaining, maybe it's fine. And it turns out for many types of texts, it works surprisingly well, especially natural language text or things that behave sufficiently random. But if you look at the worst case, then you can construct texts like this. So if the text is just all A's and the pattern is all A's but a single B at the end, you will always get the mismatch from the B. And so you'll have to try every single possible check. So the worst case is essentially n times m. If you do the exact counting, that's what you get. But in terms of the asymptotic cost, it's the product of the lengths of the two strings. Okay? Questions about brute force so far? Okay, so many of you have seen this before. Now, what do you do if your application could produce inputs like this? If both the text and the pattern are quite long, this is potentially too costly, and it's definitely annoying for such a simple task to spend so much time. If you look at the worst case here, you could say, this is really peculiar and special. There's a lot of self-similarity in the text. In this case, like A is repeated all over, so that's as repetitive as you could somehow get. Maybe we can take advantage of this instead of being hurt by it. And also, if specifically here, like if you do this as a human, you don't even, it's hard to go through and even write all the A's because it jumps in your face. Come on, you know there's another A coming. You've just seen, by this comparison, you've just seen that this is an A. Now you're asking again whether the text has an A at this position? Really? So you do repetitive comparisons in the sense that you already know the outcome. The algorithm just wasn't smart enough to realize it. So to sketch out what we'll do is well, that's a tough call. This weekend, Monday, I guess, at least. We'll look at what we can do if we study the pattern a bit up front. And it turns out even if the text is repetitive, it's enough to study how the pattern behaves to exploit that. And we'll see, well, 3 to 4 examples, depending how you want to count, for doing that. And there's a second approach, which is a different type of application. If the text is not changing all the time, and that's the realm of search engines in a way, then it might make sense to pre-process the text. Because then you can at least hope to find matches in time independent of the size of the text. And it's quite obvious if search engines for the web would do anything that has to scan the entire web for every search. I mean, clearly not possible. So we'll touch on that a bit later again. We don't need a break just yet, right? I think it's time for the first interesting algorithm of the day. I might have to prepare this, so before I start with that part, let me do that. Yeah, I remember this was a problem getting the sound to work, so I'll improvise this in a different way. We'll get to that. Don't need that today. Yeah, sorry, don't worry about that for now. In the next subsection, I want to show you the first algorithm that exploits these kind of, avoids these kind of redundant comparisons with the text characters. And for that, we'll use finite automata. So that is the point where I want to ask you how familiar you are with this. Okay, at least someone's bold. It's a roughly equal split. All right. So a third has never seen it. A third says, is that a thing? I remember something vaguely. Another third has seen it, but you know, maybe not test me right now. It is essentially just a way to view the algorithms that I'm going to explain, which I think is much more memorable. Now, it might not be as memorable if you haven't seen these before, so I'll try to briefly explain what these automata do. And then we'll see if it was effective for you. In a way, the problem is all solved for us already if you look at it from the right angle. Because if we're trying to find a pattern in a text, we're trying to check if the text is part of this language, namely the language formed by any possible string of any length, followed by the pattern, followed by more arbitrary characters. Clearly, that's finding pattern in the text. Now, expressing that's the first pattern is a little more tricky, but let's ignore that for now. We'll only use this as a vague motivation anyways. But if the text has this form, if the text is in this language, so this is probably something I haven't formally defined. We write sets of strings and then the concatenation operator to produce all possible combinations. Any string from the first set with any string from the second set, concatenate the two, that's one element of the resulting set. And so in this mixture, it's even, I should have put curly braces around the p, I guess. So is any string followed by p followed by any other string. That's all the strings in this set of strings in this language. And we check whether t is an element of that set. Now, that formulation might not have helped you too much, but if you've seen regular expressions, regular languages before, you may remember that this is a regular expression. The Kleene star is a regular expression, operation and concatenation is, and so you can write this as a regular expression. You could use any kind of programming language library for regular expressions and express that. They often have, again, different syntax, but they can express something like this. Now, theoretical computer science will tell you that, okay, if you have a regular expression, there is a deterministic finite automaton, that's what the DFA was, that recognizes exactly this language. And a deterministic automaton reads one character, does one state transition, and then it's done with its work and waiting for the next thing to be fed. So if you feed it all the characters of the text one by one, you will get the result from the automaton, yes or no, it's in the language or not. So you get this after t steps. That's almost as good as it can get, right? You need to read the text to solve this problem, so that's pretty good. So remember this guy, theoretician, says, it's brilliant. So, well, why don't you worry about this brute force algorithm, etc.? It's all done for you. Okay, I think as an abbreviation, it's fair game. All grown-ups, aren't we? So there's a few things where the programmer will correctly insist that we're not so done yet. Ignoring this zeroth problem, it's not enough to know that there is some algorithm out there. If you want to implement it, you have to also be able to write it down. And more seriously, the automaton that results from such a construction in general can be really big, exponentially big to be precise. That's a bit of a problem even in theory, right? So we don't like that too much. The approach will still work, but for somewhat interesting reasons that don't fall out of this theory automatically. If you've never seen automata before, then this hasn't helped you too much, but also don't worry too much, because I'll show you examples of the automata that we need, and then You will get enough of automata for this class. Definitely read it up because it's cool theory, but you may survive without. That's what we usually call automaton, these kind of diagrams. I'll show you how this, how that is an automaton in a second. I first want to convince you how you can do string matching with this DFA, where we still have to address the problem that this regular expression just said there's some occurrence somewhere in the text. It didn't directly tell us where the occurrence is, and it didn't guarantee that we find the first occurrence. Both of which are really no problems, but I think an example makes that clear. So treat this automaton as given to you from some super smart person and don't think about it, how to construct it for now. This is the string matching automaton for this pattern. You can always verify this by checking that there's A, B, A, B, A, C, A, the pattern written on these horizontal edges. Now, the way these automata work, they're little machines that are supposed to be in one of these states. Each of these round circles is one state that the automaton could be in. There's some indication. This arrow that comes from nowhere is the starting state, so you're supposed to start there. And what you do is, when you execute the automaton, you read the text character by character, and the diagram tells you what to do. You just follow the unique edge with the character that you see. So let's try and do that, and I'll explain the rest on the way. We start in state 0, as I said. Then we read an A, that's the first character in the text. Now, if we're in state 0, there's an arrow with A going to state 1. So after this, we're in state 1. Same thing happens now, except that now we look from this state. With an A, we stay in the same state. We're still here, but now we read a B, and that takes us to state 2. From state 2, with another A, we go to state 3. And now in state 3, if we read a C, we have to go all the way back to 0. And let's speed this up a little. Okay, A brings us to 1. From 1 with an A, we stay in 1. With a B, we go to 2. With an A again, we go to 3. And now we see something new. From state 3 with a B, we go further to 4, and to 5, and to 6, and to 7. So you can already see if you find the pattern at any point in time in the text, you just run through the states, go one state further up each way. If you ever reach this double circled state, that's an accepting state, which means you're allowed, when you end in this state, you're allowed to declare victory. You can say, I accept this input. That's the automaton point of view. The string matching point of view is, as soon as you reach this state, you can return because you found an occurrence of the pattern. And the way we do things, the way we construct these automata, will guarantee you that it's also the first occurrence. If you had seen one before, you would have reached this state before, so you would have returned back then. As an automaton, I put the sigma here, so whatever happens, you stay in this accepting state, because more chunk at the end doesn't destroy the fact that you've seen the pattern already. Is it clear how the automaton works? Now, it's called deterministic because for every state and every character, there's exactly one edge that you have to follow. So you always know exactly what to do. So there's no autonomy in this automaton. It's following exactly what you tell it. And you can completely predict what will happen. So to better understand the algorithm, the automaton, and also to be able to construct them, let's zoom a bit further in what these different states mean. It seems to have just worked in this example that once you read once you run through all the states, you get to the end. So I think the part that's kind of obvious is this chain left to right. If you are able to just step through all the states like this, especially like in this example where there's 1, 2, 3, 4, 5, 6, 7, you just go through these one after the other. It's obvious that you found the pattern. What's not so clear is maybe how do you make the automaton so that you don't ever miss an occurrence? Because you may have half overlapping half occurrences, and then you jump back because you couldn't continue your current guess. But maybe there was another guess half overlapping, and now you're not finding that one. That's the thing that could happen if you just start drawing random edges. The key insight that makes this work here is the following. You're in this state Q in a certain position, in a certain number Q. If you were able to find the first Q characters of the pattern in the text up to this position, so as a suffix of the part of the text you've read so far, you find a prefix of the pattern. And it's positions 0 up to Q exclusive, so it's length Q. The number of characters you could match is Q. And also important, there's no longer prefix of P that you could find this way. So I will many times draw sketches like this. Let's do this here as well. Here's the text, and you've really only seen it up to this point. So whatever comes after this, we don't know yet. It's a fog of war. And we try to find our pattern aligned somehow to the text. Again, there's some parts sticking out. And all these positions are matches. So I'm drawing those in green, even though this probably is not visible as green. Try to make it a little bigger at least. So these are green because they're equal, they're matches. And also this is the longest such overlap. So if you put the pattern in any other way, that's a bit, it should still overlap. So that's the pattern. If you would do that, then there's some mismatch to the text. So the state Q is the longest part of the pattern you have seen up to this point. Okay? That's the important distinction. Here's the picture in slightly nicer, but that's explaining the next step. I think it's useful to go back to the example to a certain position. Let's say we look at this part. So we've seen the text up to here, and we're trying to put the pattern in partial overlap with this in the best possible way. How many characters can we match? And so I could have put the pattern further to the back. The pattern starts with AB, so I can put it like this. That would also be a match, but this is not the longest, because I can find this longer one that has AB, AB, ACA. Now again, remember, I'm ignoring what's on this side. This is not visible. But this is longer than these two, so I'm in state 4 at this point, because the longest prefix of the pattern I can match with the text so far is length 4. Okay? Now it seems maybe at first a bit weird. How can you forget everything about the text and just remember this single number without forgetting any occurrences in the text? And the reason why this still works is that you keep track of the pattern that you've seen, and you keep track of the longest part that you've seen. So we know that the text ends with these characters. That's what this picture shows. There's the text. And we know at the end of the text so far, there's the first Q characters of P. And now we see one more character C. That's the next character we look at. And we try to decide what's the next state to go into. So our DFA always has to be in one such state. So I have to know for every new character what's the next state to go into. Now there's two possibilities. The easy one is if I can just, if I see the next character that occurs in the pattern at this point, then I'm just seeing the one longer prefix. So I go from Q to Q plus 1. That's the easy case. That's the part that we've seen before many times. So when I was at this position and I see another A, I can just extend this existing potential occurrence, partial occurrence by 1. So I go to state 5. The tricky bit is, what if that doesn't work? Then I might have to go to a much smaller state, maybe all the way back to 0, like all these long arcs here, led back to 0, basically saying I haven't seen anything of the pattern up to this point. But how do we know how far we have to jump back? So I'm looking for this Q prime, which is the longest overlapping bit with the text that I've seen so far. And the trick here is that I never need more characters of the text than are covered by this pattern here, because that was the longest occurrence. So if I have a mismatch now, the new part that I can match cannot be longer than that. Only if C is a match, but it cannot be reaching into this part of T that I've completely forgotten. That's why all the information is in the automaton that we need. The new longest match will always be shorter than Q, and that's why all the characters we need for that are contained in there. Questions up to this point? Now this is all great, but it still doesn't tell us how we can possibly find this automaton. It just lists a lot of wishful thinking properties. We would like this box to be true. We'd like to always have these states. But how to find this next Q prime is still a little unclear. I think that's a fair point for a little break. Let's do our usual. Let's do a little longer break. Oh, it works. Sounds very weird. All right, it's 5 past on my watch. Good, let's see if we can continue. So we've seen how useful these string matching automata can be. Just to emphasize that point again, because they're deterministic, every character makes you follow one edge, and so that's one step for each text character. So at least the matching bit takes time proportional to the number of characters in the text. And that's independent of what the text and pattern are like, so that's worst case, much nicer than the brute force variant. So in particular, it would work with these degenerate examples where the text's all A's, no problem. So we like those automata, but how do we get them? In the next subsection, I want to discuss how you can construct the string matching automaton and also do that efficiently, not just any way of doing it. For that, I want to come back to the second type of automaton that appeared in the Slido question much earlier. That's the non-deterministic finite automata. And these guys, they look similar to the deterministic automata. If you draw them as such a state diagram, at first sight, they might look the same. The difference is that they're allowed to have ambiguities in what to do in a certain state. In particular, they are allowed to have no edges for some letters, which means if you end up in this state and you see a letter that you cannot process, tough luck, guys, you're doomed. But that means you must have had some other option earlier on that might have brought you somewhere else. Or your input is not in the language, so the automaton should reject. Then every possible way of moving through the state diagram has to reject. But the sneaky bit of the definition is it's enough if there is one way for you to find your way through this maze of states that leads to an accepting state. So it's at first sounds not very useful in an algorithm, but let's ignore that fact. For now, the nice thing about NFAs is that they're very trivial to write down for these kind of regular expressions. We can stay in the state 0 as long as we want. At some point, we commit to move forward and read the pattern, and then we can continue reading arbitrary characters. That's as easy as it gets, right? The automaton just expresses what we said in this regular expression before. Arbitrary things, the pattern, more arbitrary things. It's just not clear how you're supposed to know when to start your journey. And so the automaton says, well, that's not my problem. If you want to accept your input, you better find a way. But it's easy to write down. Cool. That's a non-deterministic automaton. And non-deterministic because it doesn't always tell you what to do, and you kind of have to magically explore all options. I carefully avoid to say you have to explore all options in parallel, because I think that's not quite true. It's not true to the nature of non-determinism to equal it with parallelism. It's not the same notion. So I try not to say it that way. But you're supposed to try all options. We can actually use this automaton for string matching. You have to keep track of all possible histories. But it turns out this is not that hard. It's not as hard as it sounds. Because what is a history in a finite automaton? It forgets everything about the past, but except for the point that the state where it currently is. So no matter how many different convoluted ways there may have been that lead to a certain point, is all irrelevant if you reach the same state. All the rest of the past is ignored. So the set of all possible trajectories through the state diagram is at a single point in time as a snapshot is just a set of states. Previously, deterministic automaton, you were always in exactly one state. Now you're a bit more of a quantum guy if you want, but again, this is another analogy that's not perfect. But you can hover in this indeterminate state of being in several states. And until someone looks too close at you, you're undecided. Okay, again, it's not quantum. It's not in the quantum sense. There's no probabilities. There's nothing like this coming up. You can just stay uncommitted and stay in several states. You're happy to accept whenever the set of states that you're in at the same time contains an accepting state, a final state. I think this is much easier on an example than it sounds. We start in always state 0, so initially there's no ambiguity. If you read an A, well, let's look what the automaton says. I could stay here because A is part of the alphabet, or I could move to 1. So after reading the A, I'm simultaneously in 0 and 1. Pick what you want. I'm not sure yet. Okay? If you read another A, you're actually staying in the same set because from 1, if you took this transition to 1 step ago, you would now be doomed. So that trajectory just ends there and is lost. But of course, if you had stayed in 0, you can again go to 1 or stay in 0. So you're again in the states 0 and 1 simultaneously. If you read a B from here, things get a little more interesting because from 0 with a B, you can only stay in 0. And from 1 with a B, you advance to 2. So you're now in state 0 and 2. If you read an A from there, things branch out further. If you're in 2, it goes to 3, and that's the only thing. The other option was you were in 0, but then you had 2 things that can happen. So you're now in 3 states at the same time. Then sometimes things sync up again. If you read a C, the 3 is lost, so that dies out. The 1 is lost, that dies out. The only thing that remains is the 0 state, and that can only loop. So after that, you're back to only one thing is possible. And you keep doing like this. So this is the same as before. We have seen these states already. A new thing happens when we're in states 0, 1, and 3 and read a B. In that case, both 1 goes to 2, 3 goes to 4, so we advance to 2, 4. And we stay in state 0 because in this case, we always stay in state 0. There's always this loop. From here, things get even wilder. So with reading an A, you branch out into 4 different things. It's really advancing the 4, advancing the 2, and advancing the 0 to a 1 and staying where you are. If you read a C from here, we already know that the 0, 1, and 3 will die out. We've seen that before over here. But the 5 can move on to the 6. That's how we made progress. Now we're in this state 0 or 6. And with reading another A, we reach a configuration that contains at least a final state. And so we can say, yep, found a pattern. And I don't even have to trace back which of these complicated histories that I'm all lumping together now led me to this point. It's enough to know if I reach this final state, there was one. And I know at which position the match ended, so I can subtract the length of P to get the starting position. All right? So that's kind of cool. It looks like the automaton contains no information that's helpful about the pattern because it's literally just the pattern written on these funny lines, no other thought or input. But if you treat it as an automaton in this sense, stay in all possible states, and just maintain this set of states, you can actually use it for string matching. It's not a terrible algorithm. It's not the fastest either because you have to maintain this set of states. And so I guess you can probably construct automata where the set of states that you're in is fairly large, and you would always have to at least check where each of these goes. So it's not quite clear if you can do this very efficiently, but the conceptual step seems to work fine. Now again, theoretical computer science has all solved it for you. There's a theorem nihil narrote, if you have a non-deterministic finite automaton, whatever the language is, could be ours, you can construct an equivalent deterministic one from that. It's called the power set construction. It's a standard topic in undergrad classes in automata, but if you haven't seen it, it doesn't matter too much. The programmers who have seen it will rightly object that while this is cool, it's an exponential blow up in the number of states. As the term suggests, you're basically creating a DFA using all the possible subsets of states. And that sounds really expensive. So he's already giving up. But luckily some really smart people thought this through and discovered something. So there's an ingenious insight, and that's what also the KMP stands for that you've seen before, this first algorithm, or admittedly second if you want. String matching algorithm that we'll get to. You don't really have to apply this power set construction because the types of automata we're using are a bit special. To take that apart, let's see how we can go from a pattern where the last character is missing and add one more character and see if we can build the automaton inductively. So the idea is to start with essentially just the empty pattern, there the automaton does nothing. If you can do an inductive step where you can take the automaton for the first j characters, pattern p0 up to j, remember excluding, so it's j characters because we start at 0. If we have an automaton for that, maybe we can add the next character and build the DFA for the one bigger pattern. There's an easy bit, so let me draw the part that we have now, because this is a bit index mayhem. To show you again, so the pattern here is 7 characters long, but the automaton has 8 states. We start at the 0. And there's always, this is pattern character 0. So there's always the indices match between the state, and then the next outgoing right arc has the pattern character of the same index as the state had. So we have state j, and then there's a new edge labeled with p of j. That's the new character that we append. And we know where this leads to. It always goes to a new state j plus 1. So that's the easy bit. That's that part. Let's make that green as well. But we need more. We also need the case that when we're in the state j, which previously was the accepting state, right? So, okay, let me go to the example again back. Here, the pattern has length 7. That means state 7 is the accepting state, and I don't need to worry what happens in that state because it always just had this loop. You found the pattern, happily stay where you are. If I add another character at the end, this changes, and I have to worry about what to do if I don't see the correct next character. So we now need somehow these links that go back. If I find a C that is not the same as the next character in the pattern. In language notation, people write this as this transition function. So delta of j and c means you're in the state j and you read a character c. That's just the target of these arrows. So how do we find out where to go with this? And you can't just always point back to 0. Then you would overlook cases. You can do examples where that happens. You say the patterns is just b, 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 b. If you were to jump back to 0, you would miss occurrences. The insight from Knuth, Morris, and Pratt is that we can use the construction of the automaton that we already have to help us out. And let me spell out a bit to explain this, what the transition function is supposed to do. And that's, remember this box from before that we've used. What is the meaning of a state? So this new state, if I go from state J and I read a character C that is not the next matching one, I'm supposed to find the longest prefix of this string, the pattern, the first J characters of the pattern, and this new character C added. I'm supposed to find the longest prefix of that, which is also a suffix of that same string, but with the first character removed. So I'm trying to look for how much can I shift the pattern to the right, but I want the smallest amount so that I still get matches. I want these things all to match. And so, of course, this will be a suffix of the same string. And stripping one character off is just to make sure that I'm not saying, haha, I keep the exact same string. It's a suffix of itself, so I'm not doing anything. To avoid that degeneracy, I'm taking one character off. Now, because that's definitely shorter, there's no way if you just see that part. Let me rewind. This still doesn't seem to help us much. But we know we have an automaton for the one shorter pattern, and it will have to react to any kind of string in some way, but we know in what way because we know what the states mean. So if we feed the automaton that we already have with this string where we omit the first character, it will have to end up in some state J, and that state, it will have to end up in some state, and that state will not be more than J. If it was more than J, it would be J plus 1, and that would mean that C is the next matching character. But we're in the case where that's not the next matching character. So what I'm saying here is if you feed the automaton that we have so far with these characters, it will not run into the new edge. It will stay in the part that you've already constructed. And so we can use the automaton for the part of the pattern that we already have to find out this longest prefix, because that's what the states there mean. It's a little convoluted. Let me see if I can. Okay, yeah, we have to go all the way back, but I'll show it on the example that we used before. Suppose we have this part of the pattern and of the automaton. So that would be A2, because we have two pattern characters already dealt with. And now the task is, say, to find the transition from this new state to when you read an A. Sorry, that's the easy one. That's this one. The interesting one is finding, say, with a C where we have to go to, if we're in state 2, which previously was this accepting state. And so what this tells us is round and C. So in this case, we have A, B, and then C. So we strip off the first character to go to P1JC. That's just BC. And now we simulate our green part of the automaton on just this part. And there's not too much interesting happening, but it goes 0, B, C. So it reaches state 0. And that's why the edge from 2 with the C should go back to 0. Okay. I know it's the first time where things get a little hairy in the details. The trick here really is you can use the automaton you already have so far, because it does the same thing you want, and the part you've constructed must be big enough for the part for what you need. So you can do this with all the mismatch characters, and then you obtain the next larger automaton. Now this still sounds expensive if you wanted to execute it, because you would have to run many times this smaller automaton, each time going through all these characters. And it turns out you don't even have to do that. You can be even smarter here. You can, if you do this on an example, it's easy to see. All these simulations of the smaller automaton, they start with the same characters, and just the last character is different, because that's the new mismatched character. So they all do the same kind of computation up to a point, and then there's one more thing where they differ. So you might as well instead do all these simulations together and remember where you landed, and then just do the last step for each mismatched character. And even smarter, you can maintain this state. So you don't have to start simulating from scratch. You keep that state and advance it with you. And I think this is so well animated in this video by from the book that we used in Unit 2 as well, that there's no point in me recreating this. So I'll just show you this snippet from the video. I'm not sure how well the audio will work, but let's try. Here goes. Again, we'll see for steps. Batch transitions are easy. I would build those. And we're going to put a position 0. And mismatch transitions are easy. So now when we move over, X is where one of the pattern, X is where we would be if we started out without this X character, which would be the input. So we start out with 6.0, first is 0, and then we can do that without any sort of reason. So now we've got X initialized. So now what we need to do is fill in the mismatch transition for state 1. So what are they? They're what would happen if we found those characters in state X. If we found an A, it would go to state 1. If we found a C, it would go to state 0. And as you notice, that's just taking the entry corresponding to the entries we need from X's column and put it in A's column. That's all it is. Then we need to update X, which is where it would be if it maps to B. So we'll say X will stay in state 0. So now let's look at state 2. So we need to fill in what would happen if we got a B and what would happen if we got a C. Well, what would happen if we were in state X and we got a B or a C? So all we do is move those 2 zeros over to column 2. And then don't forget, we have to update X, and X goes where the machine go to column A, which is the 2 to 3. So we just move X to state 1. Now we have X in state 1, and we're doing position 3. Now you can see how simple the algorithm is once it gets going. So now the mismatch transitions are A and C. That's what we have to fill in for column 3. But those mismatch transitions are very confusing. That's where X would
of D, X goes to state 2. And again, you can check what is X supposed to be. It's supposed to be where you would be if you started the machine on the pattern with the first letter cut off. So it's supposed to be where you wind up if you got BAD. All right, so now straight forward. State 4, we have to fill in B and C. We go to X's column and copy it to B from X's column. And then we update X, that's 62A, and go to state 3. Now we're ready for state 5. We've got X and 62. And we need to do A and B, and we'll get the same 62A for 1, and 62B for 4. System is over. And then when we do C, and get the accept, that's we would do update X to get ready. And we get the state 6. We're done. And again, if this is a double check, X is where you be if you saw B, A, and A. That's the construction of the new DFA.
All right, apologies for the audio. I don't know if you could follow it. I'll cut in the original. It's not that bad in terms of the audio. It's whatever, the connection over HDMI and the speaker. I'll cut in the original video for the recording. Now the key part here is you can maintain this state X where you would have been if you read the pattern that you're building the automaton for with the first character omitted, and that automatically takes you to the position just before where you should go. So this character, this position X, state X, is not what you put in the delta function, but from there you take one more transition, and the result there is what goes into the transition function. So delta, that was what is shown in this table here, right? And if you wanted to code this, really, you see it's copying columns. So it's really easy to do this on an example, at least manually. The tricky bit is explaining why it's correct. Let's briefly discuss how well this works, even without showing detailed code for the construction. I hope that the video makes it clear enough how that code could look like. The matching part for the running time is as good as it can possibly go. You're looking at each position in the text, and you do a lookup for the DFA transitions. That's one table lookup. The time for building the DFA is a little less clear, but you can essentially do it in the time needed to produce the table. That's, again, if you follow from the video, copying the column is proportional to the number of copied elements, and updating the state X and producing the new matching edge is also constant time each. So the total time is m times sigma. Sigma is the size of the alphabet, right? That's the number of rows in the table that you have. Plus n for the matching part. And the space is obviously what you need to store the transition function. So it's the number of edges. The matching time is really, really good. If the alphabet is not too big, also the overall time is as good as you can get because you need to read the text. But it is quite a substantial space overhead to have this factor sigma in there. And so for that, I looked this up in the break. If you use all Unicode characters, then sigma with the latest release is 149,186 characters, if you want to be precise. Now, that's quite a lot if that's a multiplicative factor for your pattern. Suppose your pattern is a few thousand characters. Now you multiply this with 100K. Now suddenly this is megabytes and megabytes of table, and most of the entries will be all zeros, because if your pattern's just 1,000 characters long, most of the 150,000 emojis won't occur in it. right? It's a bit of a waste of space and time to fill all this thing with zeros. Just because potentially the text could have all these emojis, but then you would still discover that the pattern doesn't have them. That seems wasteful. So in a way, if you can guarantee that the alphabet is small, or you don't have to worry about space, this is a good algorithm. But we're not completely happy yet in the general case. To get completely happy, we have to get these three guys out again. In the next subsection, I want to show you the full Knuth-Morris-Pratt algorithm, the essence of which you have seen previously. The way to construct this string matching automaton is most of what Knuth-Morris-Pratt is. There's just this little blemish that you had to store the transition function, the edges for this automaton, for every possible input character, even if most of those never occurred in your pattern. And so the Knuth-Morris-Pratt algorithm is a modification of that avoids this overhead in space. And the idea for that is to modify the type of automaton we look at. We define a new type of transition which doesn't have an exact correspondence in the automaton world, but is very convenient at least in this case. So the third insight of those three, I don't think it was one insight per person. I think it was basically invented independently by two groups of them. Anyways, that's the historical bit. Remember how we constructed the automaton? We always kept track of this state x, where we would be if, the first character wasn't there, and where we start looking if we have a mismatch. Why would we not delay this simulation of this last step until we actually need it? So in a way, already before, we just had the current state and then the state x, and that was essentially all the information. But it's not at first clear how you can do this. The right notion for this is a failure link. That's a new type of link in the automaton, so it's an edge, but instead of a character, it has this cross mark as a label, which says no character matched. And the way these work is, if you're in a state and you see a new character for which you have an edge, you have to take that edge. If you don't have an edge for that character, you follow the failure link, but you keep the same characters. So you don't declare the C done then, as normally an automaton would. You keep the same character of the text and try again. And that could mean it still doesn't work because you only have an edge for B. So you have to take another failure link and maybe another failure link. And only at this point you can consume the C because this loop edge allows a C. Okay? So in a way, the computations are like if in a DFA. You always know exactly what to do because it's either there is an edge for your character and then you have to take it, or there's no such edge, then you have to take the failure link. No random guessing, no Schrödinger's whatever. You're not in several states. But at the same time, it's also not quite like a DFA. It's a little different. Here's our running example, this time with failure links instead of the tons of edges for all characters. I think you can already visually see that you need fewer edges. And here the alphabet was just 3 characters. Let me run through the example briefly. You start in state 0. Now I read an A. Sorry, I should have said I start in state 0 over to the left. Now I read an A, and after that I'm in state 1. I read a B, I'm in state 2. I read an A, I'm in state 3. So far, so good. And another B, that brings me to state 4. And an A, and I'm in happy in state 5, but now I read a B instead of the C, so I can't take the next edge. So instead I have to go back to 3. The important bit is I'm not consuming the B yet. I'm only consuming the B when I here can finally take the transition that has a B. That's the important distinction. I'm in state 4, read an A, brings me to state 5. I'm in state 5, I cannot read an A, the next character. So what I have to do is follow a failure link. Brings me to state 3. Now in state 3, I can still not read an A, so I have to go another failure link back to 1. And still no luck, so I have to go back to 0. And then I can read an A that brings me back to state 1. Sometimes these can cascade a bit. From state 1, I can read a B and go to state 2. I can read an A, go to state 3. Read a B, go to state 4. But we haven't passed through state 7, so no match in this case. It's a different text. Here's the same thing in nice. And that's the part I showed. Here's the pattern, how it is aligned with the text. Let's have a quick wake up. I think this needs careful reading. What's the worst case time to process one character in such an automaton as I've just shown you? At least 50 before for the other questions. I'll leave you a little bit of space, a little bit of time. Three more. 2 more. 1 more. Ah, there we go. Okay. So we have a clear winner in terms of popular vote and a few other answers, but that's the right one. So why is that the case? So first of all, why is it not constant? It would have been nice, like in a DFA, to have constant time for each character. In a way, that's true, but only in an amortized way. Remember that haunts us again from the resizing arrays. We'll come to that next week. I want to show that this can actually happen. The way that it's, why can it not be worse than M? Well, processing a character stops as soon as you take an edge that consumes that character. So you can only have more effort if you have to follow failure links, because that's the only two things that this automaton can do. One stops the processing and the other keeps going. So we have to have more keep goings for this to be more expensive. But a failure link always brings us further to the right, to the left in the picture. They always lead to a state with a smaller index, because they correspond to shifting the pattern further. So you cannot have more than M failure links. But you could have M if you have a degenerate pattern like this with all A's. So here, if you work out the failure links, they always just go one hop back. intuitively, because every position could be a match. There's nothing in the pattern. It's so self-symmetric, self-similar. It doesn't block any of the occurrences. Okay, so that sounds bad, but we'll see that this is not such a big problem. I want to briefly show the code for the algorithm, and then the analysis will probably have to wait till next week. The Knuth-Morris-Pratt algorithm is pretty much just explained, just translated the idea I explained on the automaton to code to convince you that it's easy to write this down in a way that's also efficient on computers to execute, and to make it a bit more concrete and precise. There's one function that we'll get to next week, which is computing these failure links. One obvious thing about the automaton that I haven't stated, it doesn't need a transition function for every state and every character. It just needs one failure link for each state. We don't even need these other things because it's implicit in the pattern. I know what the label of each of these edges is. It's just the corresponding character of the pattern. So all I need to store about this automaton is the failure links. So there's a function to compute those. Let's ignore it for now. And then we have an array of the failure links, which is just the target of these arrows. For a state Q, fail Q is the target of the failure link. Then we start with position 0 in the text. That's our first guess. And we start with state 0 in the automaton. That's our starting state. As long as we haven't read the entire text, we check if we can follow the match edge, which is the current position in the text matching the next in the pattern. If that's the case, we follow the match edge, which means we move I one step further, so we go to the next position in the text, and we also increment the state in the automaton. That's the easy case. If we reach that way the accepting state, we can return the occurrence that we found. And again, I is the position in the text that we compare, so you have to go back Q steps to get the return value is supposed to be the starting position of the pattern in the text, so hence the I minus Q. Now the interesting thing is the failure link if the next character does not match. So in this case, there's two options. If you're in a normal state, not the state 0, then you have to follow a failure link. So we check, we take one failure link and then check again. And this checking again is just doing the while loop iteration one more time. Right, so if we couldn't match a character, we do one failure link, and then we go back and try again, and this automatically does the right thing. If we're in state 0, then there is no legal failure link. So for state 0, we just always go to the next position in the next character in the text. In the pictures, I wrote this like this. So whenever you have a character that's not the match one, you just consume it at this point, because you have to eventually get rid of those that don't occur. So it's clear that there's a special case needed for this state 0. And that's it. Not too convoluted code, I think. And we only have this one array. I think we'll leave it for that. So failure links, how to compute them next week. How good this procedure is also next week. Because I just want to point out, as it looks from first sight, we have a loop that is repeated n times. At least it could be repeated n times, and it will be repeated n times. And we have an inner loop. So we're not always incrementing I. We could loop through this thing. We've seen that a single character might cause m failure links to be followed. So that smells like it could be n times m worst case. Back to where brute force was. That would be terrible. Now, maybe you already have a hunch that this can't happen all the time because failure links bring you back. And you can't always walk back if you have never walked the other direction. That would be the solution at the end for the analysis. But to make that formal, I'll need a few more minutes. So let's postpone that for next week. That leaves us with some minutes for discussing any questions. If you have concerns about the assessment or things like that, we can do